Now let's look at linear operator. An operator is a mathematical rule which, when applied to a function, produces another function. Okay, so when you apply an operator on any function, it produces another function because the answer you get is another function anyway. The operation of an operator L on a function U is denoted by LU. So let's say this is our function U. In fact, all the PDE we are going to do, our dependent variable or the function will always be U. Okay. And we are operating the L on that function. Okay. For example, if we let L and M, if we let L and M, here supposed to be M, be differential operators defined by L equals this. So this is the operator L and this is the operator M. Okay. Now you want to apply these operators here on the function U. You could see that there is no function here or dependent variable. All these are independent. So there's no dependence. So you want to apply this on the function. So if you want to apply that's LU, so you are applying it on it. Okay, it's like when you are multiplying something, you are applying it. Means that whatever we see here, you are going to replace it just like this. You are going to replace here by UU. You know this one, you know how to write this one. You can write delta square U delta S square as U XX minus UYY. And this one you can also write it as U X plus UY. This is the same as that. Okay. So this is the operator and this is how it is defined. So in the question they will give it to you. The definition will be given to you, then you use it. Okay. Okay. So you are going to see how we operate some of the functions that will be given to us. Okay, now let's look at this one. You are looking at, for function or operator to be a linear, it must follow this theorem. Okay, good. Or this condition, given that C is a constant and L is the differential operator, then this should be happened. The first theorem is saying that the operator operating on this function U, and there's a constant here, then if you work this and it gives you this, and also this L, the operator here operating on the addition of, these are two functions. Okay, U and V are two functions. If you also work this and it gives you this, if this one holds and this one also holds, then we can say that this is what a linear operator. You can decide to forget about these two and combine these two and gives you this. If you combine these two, that's when this operator operating on C1 multiplied by the function U plus C2 multiplied by the function V, and it gives you this. You can only use this one. If you are using this one, you use that one alone. But if you want to use this, then you have to use this and come and use this. Okay. So for this one, the C1 and the C2 is also a constant. U and V is what? Function. So when the operator operates on this and gives you this, then you can say that it is what? Linear. Okay. Now let's look at this example. Given that the operator L is this, show that the operator is linear. So you see the operator has been given. So we want to show that whether it is linear. So L is delta okay. So what is going to happen here is that we need to introduce the operator U. So normally when you are coming to solve, you have to say that let C be a constant. So even let me start from there. So you let C be a constant and U be a function. Okay. So looking at this one, you want to obey or test this law. So first one, it is L C U should give us C L U. Okay. So here, what you are going to do here is that I'm going to put this into this one. So wherever I see U, see this is the L. That is the whole of this. So whenever I say in front of this, I'm going to replace by cu. So I'm going to have delta cu over delta x plus y delta square cu over delta y squared. Okay. So let me come to the top here. C2 L V. So what you are just saying is that this one is equals to this, meaning that the property holds because let me okay, the property is here because we are saying that this one should be equals to this, and we use this one to prove. We have now gotten this one. So the property holds. Is that okay? Very good. Now let's move to next topic. So if you look at this one, this is constants. So like when you are differentiating 2x, you can decide to bring the constant out. So if I bring the c out, what do I have? I'm going to have c delta u delta x plus, if I also bring this c out, I'm going to have c y delta square u all divided by delta y squared. Now, this c and this c are common, so I can factorize it out. So if I factorize c out, I'll have delta u delta x plus y delta square u over delta y squared. Now, you see here, if I operate the lu on this, that one alone is going delta u delta x plus y delta square u over delta y squared. Okay, so this is lu. The lu is this. Okay, so what you are just trying to say is that I'm sweating. What I'm trying to say here is that this lu here, is it the same as what I have here? Yes. So it means that c, the whole of this is lu. So the whole of this is lu. So c multiplied by what? Lu. So that will be c. This one is what we proved to get this, right? Remember it is here. L. See, that's what I've proved. And when I prove this one, you see that I'm getting it because this c here, the whole of this is lu. So I'm going to have lu. Is that okay? So therefore, LCU is equals to CLU. So that's how it works. Now that is for the first side. So this one holds. So you test for this, the second one. So I'm going to test for the second one. Second one, we have two functions. So we have to define them. So you say that you let C be the constant and U and V be the function. Okay, so per the rule, the definition was given to us in the question. They gave us L in the question as delta over delta x plus y delta squared delta y squared. So LU will be delta u delta x plus y delta square u delta y squared. And then LV will be equals to delta v delta x plus y delta squared v delta y squared. Okay, so this is when I operate the L on the functions. Now, looking at this, the law is saying that Lu plus v should give us Lu plus Lv. So we are going to prove this. If you get this, then that is correct. So first thing, the whole of this one, per the property given or the operator given, you are going to have delta. Now, here is no more u against u plus v, so I'm going to put u plus v here, all divided by delta x, and here to y d square u plus v, all divided by delta y square. Here, I can split the numerator to get delta u delta x plus delta v delta x plus y delta squared u over delta y squared plus y delta squared v delta y squared. So I'll split the numerator, and remember that y is multiplied to, so it will affect everything there. Okay. Now looking at this, you realize that delta u delta x, okay, and then here too is delta square u delta. So this is u, this is u. So you bring the u together. So let's put that one together. We have delta u delta x plus y delta squared u over delta y squared plus now delta v delta x. Then it's go with the y delta squared v delta y squared plus y delta squared v plus delta y squared. Is that okay? Now, look, this one is the same as Lu. Can you see that? So here, I'll replace here by Lu. And this one is the same as Lv. So this will give us Lv. So if you look at this, this is what I've proven. And that one has given me this. So that one too holds. So we say that therefore, the operator is linear. Okay, since the true property here what holds. If somebody is using this, that one you just use it once and for all, and you are good to go. Since the true property holds, then we can say that it is what linear. All right, so let's look at properties of linear operators. So one, linear operators are commutative. Linear operators are associative property. Linear operators are also associative property. Linear operators are distributive. Now here, there are two things here. You could see that here I've written it. This is equals to this, but here I'm saying it's not equals to. This is equals to this when it is having a constant coefficient, okay? But when it's having a variable coefficient, they are not equal. So they are commutative with constant coefficient. They are not commutative with variable coefficient. So let's see some examples. Okay, now let's look at the example. This will be a little bit, or it will be a little bit longer, but stay with me. You see, for this one, per the properties, we set something that the Lm will be equals to Ml when it is what? Having a constant coefficient. But if the coefficient is variable coefficient, it cannot be equal, it cannot be commutative. So let's see. Given that L, there are two operators given L and M, and it has been defined with the function u. So you're going to have Lu, which will be putting the u there, okay, and the Mu be a function, so that Lm is not equal to Ml. And it must be truth, because you realize that here is this one is having a variable coefficient. So we are saying that it can never be true. So for you to start, first thing you have to write Lu. We know our Lu here, whereby I see this, I'm going to put it there. So x delta u delta x plus delta u delta y. Then mu will be y delta u delta x minus x delta u delta y. So this is the definitions. Now, first thing, what you are going to do is that you take this one first, you work for it, that I come and take this one, then you compare if they are equal or not. That's all. So first thing, I'm going to have L M operating on the function u. That is how you are going to do. So what it means is that the L here, where is our L? Our L is, where is it? Our L is this one, which is x delta x plus delta y multiplying by, you see this is mu. This mu here, we know it to be here. So we have y delta u delta x minus x delta u delta y. So this is what we are going to have. So you see this is multiplying this. So just like the normal multiplication, this will multiply this and multiply this, the same thing. So let me take it this way. I'm going to have x delta x outside multiplied by y delta u delta x minus x delta u delta y. You close it, plus, let me reduce the font size. So x delta x y delta u delta x minus x delta u delta y plus delta y delta u delta x minus x delta u delta y. Okay. Now, don't be confused with this. You shouldn't be confused with this, okay? It's like this. If I give you this d dx of 2x, what does it mean? Means I'm going to differentiate this 2x with respect to what? X, okay? So the same thing here, I'm going to differentiate whatever that is here with respect to x. So first thing, and remember, if I have this x is multiplying this, so it's like you are using product rule. So first thing, I'll hold x and I'll differentiate, sorry, y and d, not this one, I'm talking about the one inside. This is outside, so that one should be there. We are differentiate y and delta u delta x. This is a product rule. So first I'll hold y and I'll differentiate this one. You know what, this is already in first order, so if I differentiate second time, that is going to be, this is a x is already outside and I'm holding this, so this y will also be there. Is that okay? So if I differentiate it, that is going to be delta square u delta x squared. Now I'm now going to hold this and differentiate y. But this one, I'm differentiating the y with respect to x. You can see that. I'm differentiating the y with respect to x. And if I differentiate y with respect to x partially, it means that this y will be treated as constant, so it will be 0. So everything there goes to 0 once it is 0. Now we move to this place. Now I'm going to differentiate this place with respect to x. So if you look at this one, let me hold this one, differentiate this. If I hold this and differentiate, the x times x will give you negative x squared. Then this becomes delta squared u over delta x delta y. Okay. Now I'm going to hold this, then differentiate this. If I differentiate this, this will give me what? X. So, sorry, if I differentiate x with respect to x, that will give me 1. 1 times x will be x. So I'm going to have minus x delta u delta y. I'm done with that one. Now I'm moving to this place. Have you seen what I'm doing? Here the delta y means I'm differentiating everything with respect to y. So if everything is with respect to y, I'm going to have, let me hold this and differentiate this, okay? So this place is going to be y delta square u delta x delta y. Then let me hold this and differentiate this with respect to that will be y. So here will be left with delta u delta x. Now I'm going to differentiate this one with, let me hold x and let me differentiate this one with respect to y. That will be minus x. Then here will be delta squared u delta y squared. Now if I differentiate this one, if I hold this and differentiate with respect to this, will give us 0. So that is all. Now let's look at those that are like terms. We can group them together. This delta squared u delta x squared. Delta squared u. So I think this one does not have any like term, but this one, delta square u delta x delta y. Then we also have delta square u delta x delta y. We can put that one together. Then this one is delta u delta x delta u delta y. You can't put anything there. So the only thing you can put together is this and that, right? So let me write this one. This is xy delta square u delta x squared. Then this and that you can put together. So that will be plus bracket open y minus x squared delta squared u delta x delta y. So this and that. Now here will be minus x delta u delta y. Then, okay, this is delta u delta y and this is delta u delta x. So they are not the same. Plus delta u delta x minus x delta squared u delta y squared. So this is the first one. Now let's prove the ML. This ML. So we are going to prove that one. So we are going to look at MLU. So this time around, the operator is going to be on L. Okay, so we are going to write the M operator. Where is our M? Our M was y delta over delta x. You can check it from the question if you have screenshot it. Minus x delta y. And this one is multiplying by LU. This is our LU. Okay, so here the same thing, right? Y delta x bracket open x delta u delta x plus delta u delta y minus x delta y x delta u delta x plus delta u delta y. So this is how it's going to be. So let's see. Here means I'm going to differentiate everything partially with respect to x. So I hold x. So if I hold x, automatically this x will multiply with this. That will give me xy. Then I will differentiate this with respect to x. That will give me delta square u delta x squared. Then now I'm going to hold this and differentiate with respect to x. That will give me 1. Leaving the y, so plus y delta u delta x. Now we move to the next one. The next one, remember that the coefficient of delta u delta y is 1. So first, if I hold 1 and I differentiate this one, that will give me, with respect to x, so that will give me y delta square u delta x delta y minus, because I don't need to do the other side because The other side is constant one. If I differentiate one, that will give me 0. So there's no need of doing that. Then the next one, this one, with respect to y, so if I hold x here, this x multiply this, that will be x squared. Then differentiate this one, that will be delta u, delta x, delta y. Then I will also, you see, because of negative, everything will be negative. Now I'm going to hold this and differentiate this. With respect to y, it will go to 0 because that will be treated as constant. Now let's move to this place. If I move to this place, I'm going to differentiate. You know already, if I'm differentiating the constant with respect to y, that will be 0. So I don't need to do that. So let me differentiate this one. So if I differentiate this one, that will give me negative x delta square u delta y square. Okay. Now let's look at those that are the same so that we can group them together. This is delta square u delta s squared. Do you have something there like that? Delta square u, no. But okay, this and this are the same. So this is what you are going to do. You write this one, x, y, delta square u, delta x squared, then plus y, delta u, delta x, plus this and that are the same. So I write this as y minus x squared, delta u, delta x, delta y, then minus x, delta square u, delta y squared. So now let's compare them. First one, we have xy delta square u delta x square. It's also here xy delta square u delta x square. That one is the same. Then here we have y minus x square delta u delta x delta y minus x squared delta u delta square u, they're supposed to be square. Delta square u delta x delta y, they are the same. Then we move to the next one. This is negative x delta u delta y. We don't have some here. We have delta u delta y. We don't have some here. Negative x delta square u delta y squared. We have some here. So you see, there's something that is here that is not here. So therefore, we can say that L M U is never equals to L M L U. So it is not equal. So that is the proof. Is that okay? Very good. Okay, now let's look at our last example. Show that the use of script x, that's first derivative, that the partial derivative of x, u with respect to x, y use as script y minus x, y squared plus sine y equals 0. It's a linear PDE. So we want to show that. Okay. Now, when you have to do this, we only pick the principal part. When you say principal part, is the one with the derivatives. The ones without derivatives are not part. So you only pick the principal part to test. So this is with derivative. This is with derivative. This does not have any derivative. This does not have any derivative. So the principal part here is ux plus y u y. Okay. Now this one can be written as delta u delta x plus delta y delta y delta u delta y. Is that okay? So we say that let lu to be equals to delta u delta x plus y delta u delta y. Is that okay? Now I want to use the combination property to prove, or the theorem. The combination one says that L of C1U plus C2V should give us C1LU plus C2LV. Okay, where the L, I mean the U and the V are functions, and that of C1 and C2 are constant. So if you're able to prove this to be equal to that, then it is linear. So let's start. Here, we are just going to substitute here. So wherever I see u here, I'm going to replace by the whole of this. That's the meaning. So here is going to be delta bracket open C1U plus C2V all divided by delta X plus Y delta bracket open C1U plus C2V all divided by delta Y. Okay. Split the numerator. That is going to give you delta C1U over delta X plus delta C2V over delta X plus Y delta C1U over delta Y plus delta C2V over delta Y. So now, here the C1, you have to factorize it out. So that's the constant. So C1 out. You have delta U over delta X plus C2 out. You have delta V over delta X plus you have C1 Y out delta U delta Y plus C2 out delta. Okay, so Y have to be here. Okay, this Y is multiplying through. So here to be C2Y delta V delta Y. Now here, let's take the one with the U together. So this one is having U, this one is having U. So let's put them together. So C1 delta U delta X plus C1Y delta U delta Y plus C2 delta V delta X plus C2Y delta V delta Y. Now C1 and C1 are common, so I'll bring it out, leaving delta U delta X Y delta U delta Y plus C2 out delta V delta X Y delta V delta X. So this is what we have. So C1. Now remember delta U delta X plus Y delta U delta Y is the same as LU. Okay, so this place is going to be LU plus C2. If I'm to bring the LV here, it will be the same thing. Delta V delta X plus Y delta V delta Y. So it means that here it will be. So what you are just saying is that this one is equals to this, meaning that the property holds because the property is here because we are saying that this one should be equal to this, and we use this one to prove. We have now gotten this one. So the property holds. Is that okay? Very good. Now let's move to next topic.